State-of-the-art robotics simulators operate in discrete time, taking fixed-sized time steps. Discrete time simulation can be fast and effective, but the user must specify the time step. If the time step is too large, the simulation can have undesirable artifacts. But if the time step is too small, the simulation runs slowly. Meanwhile, continuous time error-controlled integrators automatically adjust the time step to maintain stability and a desired accuracy. Error control is widely used in engineering for applications from circuit simulation to orbital mechanics. But existing error-controlled integrators struggle to handle the stiff dynamics of rigid contact while meeting the fast real-time requirements of robotics simulation. In this paper, we present a new convex error-controlled integrator for robotics, which we call CENIC. CENIC combines the best of error-controlled integration and convex time stepping, as illustrated in these test simulations. CENIC is orders of magnitude faster than existing error-controlled integrators, making it suitable for robotics. At the same time, CENIC maintains strong convergence and accuracy guarantees via error control. CENIC performs particularly well on problems with many stiff contact interactions, where existing error-controlled integrators struggle. We also show how to simulate complex user-defined system blocks, like controllers, planners, and safety filters, while maintaining convexity. This allows us to simulate strong custom force elements, like this vacuum gripper, with implicit integration, avoiding the pitfalls that would force a discrete time simulator to use small time steps. Continuous time simulation with CENIC also allows us to model objects with different static and dynamic friction coefficients. Rigorously modeling these effects is not possible for discrete time simulators. As an example of different friction coefficients, we raise this platform slowly until the block starts to slide. With a single friction coefficient, we can match the angle where the block starts to slide, but then it slides too slowly. With separate coefficients of static and dynamic friction, we can match both the sliding angle and the sliding speed. Even with the added computation of error estimation and step size selection, CENIC achieves simulation speeds on par with state-of-the-art discrete-time robotics simulators, like MuJoCo, Drake, and IsaacSim. We tested CENIC's performance with a real-to-sim experiment. First, a teleoperated robot drops several objects into a bin. Then, it dumps the contents of the bin on a wire dish rack. We play back the same actions in simulation. This scenario is particularly difficult to simulate. It includes large mass ratios, non-convex geometries, thin objects, and high-speed collisions. With error control, CENIC completes the 100-second simulation without obvious artifacts in about 30 seconds. A real-time rate over 300%. On the other hand, discrete time simulation exhibits major artifacts, with time steps of 20 milliseconds, 10 milliseconds, and even 2 milliseconds. Only with a very small time step of 1 millisecond does discrete time simulation avoid artifacts. With this small time step, the simulation is over twice as slow as real time, and about 8 times slower than error-controlled CENIC. We hope that convex error-controlled integration will provide a new foundation for fast, physically consistent robotic simulation. By separating numerical errors from modeling errors, CENIC opens the door to better sim-to-real transfer in manipulation, locomotion, and beyond.